Hi and welcome back. In this video, we're going to talk about increasing and decreasing, and specifically what they look like on a graph. So there are some pretty formal definitions of increasing and decreasing in mathematics, and honestly, they're way more complicated than we need, and it can make it really messy if we work on those specific definitions. So instead, I'm just going to use a more casual or intuitive approach. So we say that a function is increasing if the graph rises as we move from left to right. So as we go from left to right, we're going up on the graph. The more formal way to say this might be that the output values increase as the input values increase. Graphically, going from left to right, we'd also be going up, and so you can see the little portion of the graph might look like this, where the input is increasing and the output is also increasing. Then we say a function is decreasing if the graph falls as we move from left to right. So similarly, a more formal way to say this would be that the output values decrease as the input values increase. So this means graphically, if we go from left to right, our output values would be decreasing. And so the graph would look like this in that it is falling. The input values increase, but the output values decrease. So again, these are pretty intuitive ways of thinking about it. Increasing is that the graph is rising as we go from left to right, and decreasing is if the graph is falling as we move from left to right. Let me show you what this looks like on a graph. So I'll draw a graph here, and let's say we also have these values A and B that are some inputs, so I'm just labeling a couple values on our x-axis. So this first section of the graph, until we get to A on the x-axis, is decreasing. So moving from left to right, the graph is falling. Then from A to B on the x, the function is increasing since the graph is rising. And then at B on the x, we start to decrease again since the graph is falling. So one way I like to think about this is as if I'm walking on this graph, like it's a mountain or a hillside or something like that. So walking from left to right, for the first section of the graph, I'm walking downhill. Then when I get to A, I start walking uphill until I get to B, at which point I walk downhill again. So the downhill portions are the decreasing part, and the uphill portions are the increasing part. So let's talk a little bit about how we would write this mathematically. So remember here, we have our x values as our input, that's the horizontal axis, and then we have y values as the output, that's the vertical axis. Then when we're talking about increasing and decreasing, we use interval notation to refer to the input values specifically. So you'll notice that I was talking about A and B, which are labeled on the x-axis. This is just what we use to help orient ourselves. We use the x values as our locations where we're talking about increasing or decreasing. Then you'll notice that there are locations where we're changing from decreasing to increasing or vice versa. So at these points where it's changing, we say that it's neither increasing or decreasing. So at the points where we're switching, we don't include those as increasing or decreasing, and so because of this, we always use parentheses. That's sort of like being at the bottom of a hill, we're not going up or down, and at the top of a hill, we're not going up or down, so we don't include those values, and anytime we're not including an endpoint, we use parentheses on our interval. So anytime you're doing increasing or decreasing, use parentheses. These two notes basically give us what we need to know for writing increasing and decreasing intervals. We use interval notation and we use parentheses. So let's do this for the little sample graph we drew here. For increasing, this corresponds to x values in the interval A to B. So remember, we're looking at input values, and the increasing interval starts at A and ends at B. Then for decreasing, we're looking at x values in the intervals -infinity to A, so that's everything up until we get to A, and then from B to infinity. So personally, I actually write a union symbol to union these two intervals. If we're starting to use more complicated definitions of increasing and decreasing, we need to be more careful about this, but in these instances, it's just fine to use a union, at least in my opinion. So we're going to union these two intervals just to say that we're looking at both of them. So we're doing negative infinity to a, unioned with b to infinity. And this is where the function is decreasing. Now, before we do another example, I just want to highlight these points where the function is changing from decreasing to increasing and from increasing to decreasing. These locations are special, and so we have a special name for them. Specifically, we say that a local maximum occurs at a point where the function changes from increasing to decreasing. So it makes sense that it's a maximum since we're going up and then down, sort of like being at the top of a mountain. It's some sort of maximum in a local area. So you can imagine that you might climb a mountain, you're at the top, you're at the local maximum, you're at like the highest point in the area. You might not be the global maximum, you might not be at like the highest mountain in the world, but you're at a local maximum place. So we have local maximums anytime the function changes from increasing to decreasing. So when you're going through increasing and decreasing, anytime this happens, that point is a local maximum. Similarly, we have local minimums anytime the function changes from decreasing to increasing. So this is like a valley, we're going down and then up. Anytime this change happens from decreasing to increasing, that's a local minimum. So let's talk about what this looks like on the sample graph we had. So our graph changed from decreasing to increasing at x equals a, and from increasing to decreasing at x equals b. So that change from decreasing to increasing at a, we would say that that is a local minimum. So we'd write a, f of a is a local minimum. So this is assuming that the function is, let's say, y equals f of x, and then the corresponding output that goes with a would be f of a. So a, f of a is the point, and that point is the local minimum. Then similarly, we'd have a local maximum at b, f of b, and that's because at x equals b, the function is changing from increasing to decreasing. So b, f of b is a local minimum. All right, so we have increasing and decreasing, and we have local minimums and local maximums. Let's try this on an example. Let's consider the graph of f, and I'll put it here. You'll notice that f is a function since it passes the vertical line test, and we're just going to answer some questions about it. So for what values of x is f increasing? For what values of x is f decreasing? Which points are local maximums, and which points are local minimums? Okay, so I'm just going to walk on this graph from left to right and label each part as increasing or decreasing. So as I start, I'm decreasing, so I'm going downhill until I get to x equals 0. Then I'm switching and going uphill from 0 until I get to 2. And then at x equals 2, I'm going to start going downhill or decreasing again. So for increasing, I'd see that this happens on that inside interval. So from 0 to 2 on the x, those are the x values where my function is increasing. Then for decreasing, I'm seeing that we're decreasing from negative infinity to 0, so that's that entire left part of the graph, and then from 2 to infinity. So we're decreasing for the first part and for the end part. You might notice that in the sample graph we did, we also had decreasing on the outsides with increasing in the middle. This just sort of happened that way. It could easily be the other way where you have increasing, decreasing, then increasing. You could have all increasing, could have all decreasing. There's lots of variation here. We'll be practicing these concepts with different functions, but for now we're just getting used to them. All right, so now we need to know which points are local maximums. So maximums occur where the function changes from increasing to decreasing. I'll see this happens at x equals 2, and specifically at the point 2, 2. So 2, 2 is my point, that's the local maximum. Then for local minimums, this is where we change from decreasing to increasing. I see that this happens at x equals 0, which corresponds to the point 0, 0. And that's where my local minimum occurs. All right, so this is an example of how we do increasing, decreasing, and local maximums and minimums. I just want to make a couple notes before we end the video. So something that is important is context. So in these cases, intervals and points will look the same notationally. So in the example we just did, we had both points and intervals as our solutions, and they look exactly the same. So without context, we might not know what's happening. So let me tell you more about what I mean. We could have A, B in parentheses, and A, B in parentheses, and these could refer to different things. So A, comma B could refer to x values from A to B, so this could be an interval, or it could be an ordered pair, where we have x equals A and y equals B. So it's important to note when we're having intervals or when we're having points. So this isn't a problem, this isn't bad, it's just something to be aware of when we're doing this. So my recommendations are to use extra language when necessary. So if you're unsure about your communication, just try to write in some extra words or some other way to indicate really what you're talking about. Additionally, it's good to always check what the problem is asking for. So the different ways the problems are worded might be asking you for x values, they might be asking for intervals, they might ask for points, they might just ask for the y value, that sort of thing. So as long as you're aligning your solution to what the problem is asking for, that's good communication. So if it asks for an interval and you write A, B, we can assume that that is an interval. And lastly, I just want to say a reminder that math really does involve communication. So do whatever you need to communicate. There's no right or wrong way to do this. And there's always going to be some cases where two things look similar but mean different things, and we just need to explain them. So all right, that's it for this one. Thanks so much for watching, and I will talk to you in the next one.